I have a rig here. Okay, it's holding up a load of 16 kilonewtons at a distance 4.8. This X given here. Uh, the rig has a cross member itself that has a weight of 5.4 kilonewtons at 2.6 over like this. Okay, if the tension in the cable going through here is 18, I want to find basically what's going on at E here. So what is all of the reactions at E? So we'll start by drawing my free body diagram of this guy, like so. Okay, and we'll start with our 16.2 right here and our 5.4 right here. And first thing I want to do is let's talk about my reactions, right? This is rigidly attached. I can't the motion upward, to the right, or a moment. They're all restricted. I can't do anything at E because it's basically welded into place there, right? So I've got what I will call an EY value, an EX value, and a moment at E given like that. Okay, now let's talk about this cable. Now, you may be tempted to put a tension like that, okay, because it's pulling up on that member. But keep in mind that cable is connected over here as well. So even though those two cables are, even though the cable is there, I don't need to include it because it's an internal force. That is, it's connected at 2 points on the body, right? So when I sum the forces, they're just going to cancel each other out anyway. Similarly here, you might think, oh, I've got a force that way, but I've also got a force pulling up like that. Again, that cable is attached on the body, okay? So it's always what we talk about is summing or drawing all the external forces, okay? That tension, it's there. There is a tension force there, but it's internal to the body. The tension is acting at 2 points on the body, thus canceling each other out, and I don't need to worry about those tensions. Now, if I look here, I've got this tension going down like this, and then if I think about down there, now that reaction force, the force at F, is actually external, right? So that would not be part of this. This would not be included in the free body diagram. Only that force there, that's where the 18 kilonewtons will be placed. Okay, so we only draw external forces on the body. Okay, so if you've got a cable, you've got a force internal to the body, it is not included because there's going to be, every force has an equal and opposite force coupled with it, right? So if it's internal, then there's going to be a coupling force on the inside that's going to just cancel itself out. So we don't need to worry about including it. We only put those external forces. Therefore, we only put the 18 kilonewtons at point C because it connects to that cable connects somewhere outside of the body. Okay. Now that I have this, I can go ahead, sum my forces in the X direction. Okay. The only force I have in the X direction is EX, so it has to equal 0. Very simple, very trivial. Some of the forces in the y direction, now I've got EY acting up, and then I've got 16.2, I've got 5.4, and I've got 18 all acting down. From that, I can then solve that the vertical reaction at EY is 39.6 kilonewtons. Lastly, I have to do a moment. Okay, let me do the moment at E to get rid of EX and EY. I know them now, but I may as well do it there to get so they don't even show up in the equation. Okay, you don't want to forget to include the couple moment here, which is what I'm actually looking for, which is that couple moment about E resisting the rotation as it's welded into the ground there, as it's sunk into the ground like that. Then I just basically have those three R cross Fs, which are all going to be horizontal distances times vertical forces, right? So I have that 4.8 distance times 16.2. That's creating a counterclockwise rotation, so it's positive, as is the 5.4, which is 2.6 away. And then the 18 is on the other side, so it's going to be negative, and that's going to be negative 1.5 times 18 equals 0. Solve this one for the couple about E, and I get negative 64.8, and that's going to be kilonewton meters. All the all the negative sign means is I drew my reaction moment, the moment at E, that couple moment at E, I drew it in the wrong direction. I drew it counterclockwise. It's actually a clockwise moment. So I could flip that, leave it at negative, but that's all the negative means. So if you make an assumption about an unknown force, if you're wrong about the direction, you just flip the arrow. It's actually going in the other direction, okay? But the other key thing on this problem is recognizing that those internal forces, any forces that are internal to the system, do not need to be included in the free body diagram, because there's a force on the other, there's another force that's just going to cancel that out somewhere within the body if it's an internal force.